Hi, this is Mr. Heineman from Evergreen High School, and this is for my Computer Science Discoveries classes. This is Code Studio, Unit 2, Lesson 7. So when it comes to the distributive property, that's when we have two terms on the inside here and a number on the outside, or another term on the outside that we're going to multiply by the whole set of parentheses. The way we deal with that using the distributive property is, since there's two terms on the inside, we're going to multiply this number by both terms. And that way we know that the whole thing is getting multiplied by this number. So 6 times x, you just smash those together for 6x, and then 6 times 5 is 30. Okay, so when we distribute, that's why we call it the distributive property, we're multiplying everything on the outside of one set of parentheses by everything on the inside of the other one. And so when we multiply 4 by this term, 2x, when I have a number in front of x, I just multiply the two numbers and leave the x alone. And then multiplying by negative numbers, well, positive times a negative is negative, so we can just write minus 24. So speaking of negatives, when we have a negative on the outside, that negative goes with the number when we multiply. So negative 3 times 2x is negative 6x, because negative 2 or negative 3 times 2 is negative 6. And when we do negative 3 times 5, that would be negative 15. I could just write minus 15. I wouldn't have to write plus negative 15. I can just go right to minus 15. That's a little bit easier. Similarly, when we have negatives on the inside and we're multiplying by a negative on the outside, we got to remember negative times negative is positive. So negative 5 times negative 3, positive 15. And then negative 5 times negative 6 is a positive 30. Okay, and so we use the distributive property whenever we have something on the outside of a set of parentheses and multiple things on the inside of another of the parentheses. That way we make sure that whatever's on the outside gets multiplied by everything on the inside. So when it comes to variables, variables are, simply put, letters or other symbols that represent some quantity. What that means is it's like a placeholder until we either know what the quantity is or we can choose what the quantity is and substitute. But what we're going to be doing is just using it as that placeholder. We can only combine terms if they have the same variable with the same power. And that's really important to know. So we can always combine numbers together, but we can only combine terms that have variables in them if they have the same variable with the same power. And so we're going to practice using variables to combine like terms and things, but also when we multiply two variables together. We've been multiplying numbers and variables. That's easy enough. We just smash those together or multiply by numbers in front of variables. When we multiply variables, there's some special things we have to consider. So when it comes to multiplying variables, we're going to use the distributive property as an example of this. When we multiply the two variables, we distribute this x to both terms. So when we multiply by x by x, we're keeping in mind that we're doing a different operation. When we add x and x, there would be a quantity of 2x's, which is what a coefficient or a number in front of a variable would represent. But when we multiply, that's different. We're multiplying, and when we do that, we write an exponent to represent how many times we multiplied that variable. In this case, x times x is x squared, because it's x times x, there's only two x's. So that would become x squared, and then of course x times 2, they're not both variables, it's just 2x, because we're doubling x essentially. When it comes to variables that already have a an exponent on them. So this has a 2. We would pretend that this exponent is a 1 here. And what we do is when we multiply, since x squared represents, as we said before, x squared means it's x times x, which also means that if we multiply x squared by x to the 1, that means we have that x squared, and then we're adding a third x. And really what ends up happening is we add the 2 powers. It's a quick short way of doing it. So x to the first times x squared would be x to the third, because that's 1 plus 2. And then we can also again multiply x times 2. If this were x squared, it would be 2x squared instead of 2x. So now we'll talk about combining like terms. So when we have big expressions like this, and we have to talk about combining like terms, and as I stated before, you can only combine terms if they have the same variable and the same power. So first thing we're going to do here though is we are going to distribute twice. So we're going to distribute x in this first expression and then 4 in the second one. Okay, and so when we do x times 5 is 5x. Remember, x times x is x squared. 4 times x is just 4x. And then of course 4 times 2 is just 8. So now I have 4 different terms, 5x, x squared, 4x, and 8. They're all being added, which is helpful to me because I remember from earlier that we have those associative and commutative properties that allow us to do things with terms as long as we're adding or multiplying. Which means that if I'm going to combine like terms, in this case our like terms are 5x and 4x. There's no other x squared term, and there's no other numbers to combine with either the x squared or the 8. So we're going to ignore those, and we're going to combine just the 5x and the 4x. However, we notice they're not next to one another, and that's usually how we want to combine like terms. So what we would do is we want to move the 5 here, which means we got to switch the 5 and the x squared, which I'm allowed to do because of the commutative property. So I'm going to rearrange those using the commutative property, and that way I have the x terms together, and then I can use the associative property to group them as a single unit. Essentially, that's what grouping does, because I'm going to add those anyway. And when I combine them, I'm just adding the numbers in front. Those are called coefficients. We're just adding those two numbers to get 9x. And then I still have plus 8. So when it comes to combining like terms, remember we can only combine terms that have the same variable to the same power. I can't combine an x squared with an x because they don't have the same power. And of course I can't combine numbers and variable terms because they don't have the same variable. Numbers don't have a variable at all. So we just got to remember that and keep that in mind when we're eventually solving in standard 2.1, but in here when we're rearranging, we're just making sure we're combining just the like terms and not terms that are not like. So we're going to do some examples now, and this first example is an example of what we call a two-column proof. And the way it works is that the two-column proof shows a list of expressions, and then right next to is the list of properties that allows me to write that particular expression. So when I write something here, it's going to be whatever the reasoning is over here is why I can write it. So sometimes I'm given the properties, and I'll have to look at my expression and see how can I change the expression here to write a new one here that would show that I used this property. as a reason why I could do that. Or sometimes we're given the expression, we have to actually identify what property or properties we could have used in that step. So over here, we're going to start with 1, and I look over here, I'm given the property as given. Okay, and that's not really a property, it's the definition of what I'm starting with. And in this problem, I'm given this expression, which you'll recognize from a previous example. So this shouldn't be really all that new, but we'll use it and we're going to prove what we just showed. It's just a more formal way of doing this. So when we prove this, we are showing all the expressions and all the reasons over on 2 different sides. So if that's what's given, then that's what I'm going to write. X times the quantity 5 plus x plus 4 times the quantity x plus 2. That's exactly what is up here in the given, and is exactly where we're starting our proof. Because then in the next step we're told that we can justify it with the distributive property, which means I'm going to use the distributive property here to multiply, and I don't necessarily need to draw my arrows. I can just show that I multiplied everything, and I could show that by just writing out the terms. 5x, remember x times x is x squared, 4 times x is 4x, and then of course 4 times 2 is 8. So now I have just the 4 terms, and we notice that there's now an expression here that is a transformation of this. It shows, first of all, it's in a different order. The 5x and the x squared have been switched. And also we've got parentheses around the 5x and the 4x. And so remembering back to the beginning of this unit in this video, we can rearrange terms using the commutative property. And in this case, because it's addition, we would write commutative, and we can abbreviate if we need to. So that's why we can rearrange. And then we also added parentheses. So actually that's a second property. So I'm going to add, it's also the associative property because it has to do with grouping. And that one is also of addition because we're doing addition here. So we've grouped them together. Now it says that our last step is the reasoning we give is just combining like terms, which means I'm only combining the like terms. I notice there's an x squared, there's an 8. Those don't have like terms because there's no other x squareds. There's no other terms that have the same variable to the same power. Same with 8. There's no other numbers, which is essentially the same variable to the same power. We can just combine the 2 terms on the inside. So I rewrite x squared, 5x plus 4x, I just add 5 and 4 to make 9x, and then plus 8. And that means I'm finished because I've filled in everything. And I look up here and I have the same expression as we were going for. So we've proven that this expression can become this expression using these properties. So the last problem was an example of a multi-step problem, but it was in a proof form. We're just going to do a multi-step problem in this one. So, and what that means is just going to require us to do more than just like 1 or 2 steps to simplify this. And when we say simplify, we mean we want to get it down to where we have no more like terms. Remembering that like terms are always the same variable to the same power. So I'm going to look first, can I do a distributive property? Because I know that the distributive property will take something that I can't really work with and transform it into something I can work with, because it'll just be 2 terms. So I see there's a distributive property here, so I'm going to multiply the 5 through. I'm also going to remove the parentheses around 2p and 4 so that I can rearrange this in an order that makes sense for me. because I want to put like terms together before I add. And I can always rearrange the terms however I want using the commutative property. In this case, we're just going to switch 4 and 5p. That'll be an easy way to get the like terms together. And once I have those like terms together, then what I can do is use the associative property to group them into groups of like terms. And that way I can really see, it's really for my eyes, to see that these two are like terms, those two are like terms. They're going to become one term that we can combine. 5 plus 2 is 7. And then 4 plus 5 is 9. So our simplified expression is 7p plus 9 from this. And it took us a few steps, took us 3 steps. And if you want to technically add, like I could add the parentheses and call it a 4th step. But it took us a few steps to get to this point. So we're going to be multiplying polynomials. And in order to multiply polynomials, we need to remember about multiplying variables. And so we're going to do a quick set of practice here. So remember, when it comes to multiplying variables, we're going to end up with exponents, and exponents represent how many times we've multiplied. And the shortcut method is to take the two exponents when I'm multiplying and add them. Right? I don't do that when I add two terms that are variable terms, because I can only add like terms. First of all, they have to have the same power. So if they didn't have to have the same power, there wouldn't be a reason why I wouldn't think about the exponents. But since they have to be the same power, we would just add the two coefficients, and then leave the power alone. When we multiply, though, we're adding the two powers. So x to the first times x squared, that would be x to the third. I would just add the two powers, and I wrote a little 1 to remind myself that x by itself means there's a power of 1. So when I already have powers, though, I'm just going to add the 2, right? 2 and 3 would be x to the 5th. Okay. When I have coefficients in front of x, what I do is I treat them kind of separately. So I multiply the coefficients, and then I multiply the variables. And that's it. So we need this in order to multiply polynomials, because polynomials have multiple terms, and if they have more than 2 terms, then you're guaranteed to have some polynomials with powers other than 1. And we typically write those polynomials in descending power orders, so the highest power first and so on down the line. So when it comes to multiplying polynomials, we have to make sure that we multiply everything inside this set of parentheses, so for this polynomial, by everything in this polynomial. A polynomial is just a set of terms that all have the same variable, and each term will have different powers. And it's all in what we would call lowest terms, which would mean that there's no like terms that we can combine. So one of the ways we can do that, so that we make sure that we multiply everything in here by everything in here, is to use this box, or we call it an area model. And what that means is that we're going to take this polynomial, we're going to write it across the top of here. X cubed plus 6x squared minus 5 here. And then on the side, we're going to write the second polynomial, 2x plus 4. And then each square, or each box here, will be the area, essentially, of that spot, which this length is represented by x cubed, and then this height is represented by 2x. So I would multiply x cubed and 2x. And so then, remembering that this is an x to the 1, I'm going to have 2x to the 4th, because I add the two exponents. Same thing here, we get 6x squared times 2x. And so 6x squared times 2x, 6 times 2 is 12, and then it's x to the 3rd. And then we have negative 5 times 2x, which is negative 10x. And then we repeat that with the second term of this polynomial. So we go x cubed times 4, which is just 4x cubed. Then we have 6x squared times 4. And again, we're just multiplying the two numbers, leave the x squared alone. And negative 5 times 4 is negative 20. Then to write our final polynomial, we combine any like terms. So in this case, 2x to the fourth doesn't have a like term. It's just 2x to the fourth. These are two like terms, so we're going to add those and then write it in our polynomial. So we have 12x cubed plus 4x cubed. That's 16x cubed. The x squared here doesn't have its own, or doesn't have any like terms, so we just write it. The negative 10x also doesn't have a like term, so we just write it. And then the negative 20 is its own term also, it doesn't have any like terms. So our final polynomial is this. 2x to the fourth plus 16x cubed plus 24x squared minus 10x minus 20. So another way to multiply polynomials is to simply use the distributive property. And that means everything in here gets multiplied by each term in here. So we would make sure we multiplied these two, and these two, and these two, and then we would repeat that with the other term. Sorry, I gotta go all the way to 1. There we go. So we'd go, and each of these would be multiplied by each of the two terms. So when we do that, 2x cubed times x to the, or times 4x is 8x to the fourth. And then negative 4x times 4x is negative 16x squared. 5 times 4x is 20x. And then we go to the other side and do negative 1. So we got 2x cubed times negative 1 is negative 2x cubed. Negative 4x times negative 1, positive 4x, because the negative times a negative is a positive. And then 5 times negative 1 is negative 5. Then we rearrange this in order of powers. So 8x to the fourth gets to stay in front, but because of the commutative property, we can rewrite this. And so then next comes the x squared term. Now I notice I have two x terms. So I have some like terms, and if I have any like terms, I need to combine those. So I'm going to use the associative property to group them and then just add them. So our final answer has no like terms in it. That's 24x minus 5. So final answer, done. So now that we can multiply polynomials, we can apply them to a problem, and that's what our exceeding level is. So we look at this problem and we're trying to find the area of the shaded region. And I noticed that the area of the shaded region is really, it's like I took a big rectangle and then I cut out part of the middle of it in a rectangular shape. And so if I take the area of the large rectangle and the area of the small rectangle, and I subtract the area of the larger one, or I subtract the area of the smaller one from the larger one, that will give me the area of the gray shaded area. Which means I have some math to do, because the area of a rectangle is length times width, so I would do x plus 5 times x plus 9 for the big rectangle, and make sure I multiply everything here. So x times x is x squared, 5 times x is 5x, x times 9 is 9x, and then 5 times 9 is 45. And then I can combine these two like terms, because they're like terms, they have the same variable, the same power. So add those two to get 14x, and there's my final area of the large rectangle. So the smaller one is then x plus 4 times x plus 7. Same thing, x times x, 4 times x, x times 7, 4 times 7. So now we got x squared plus 4x plus 7x plus 28. And then combine these two like terms, x squared plus 11x plus 28. So now I'm going to subtract the two. Larger rectangle first, and then minus area of the smaller rectangle. And then what that means is that this negative sign is going to distribute like a number would to those three terms. And then I can rearrange by pairing up terms with like, or pairing up the like terms, I should say, as long as the negative goes with these terms. So x squared minus x squared, 14x minus 11x, 45 minus 28. And so then I can do those individual problems. X squared minus x squared is 0. I don't need to write 0 unless I find out the whole thing's 0. 14x minus 11x is 3x. 45 minus 28 is 17. So the area of the shaded area, on the shaded region I should say, is 3x plus 17. And I did that by finding the area of the larger rectangle and the area of the smaller rectangle and subtracting the area of the smaller rectangle from the area of the larger rectangle. That's it for standard 1.1. Good luck on any test or reassessment you're doing.